Thank you for joining us on Synthesis Workshop. In today's installment of our Advanced Organic Chemistry course, we're joined by Patrick Deneny. Patrick completed his master's at Roche in Basel, where he worked on the optimization of cross-couplings and heterocycle synthesis for biologically active molecules. He subsequently carried out his graduate studies in the Kant Group at the University of Cambridge, and currently he works at the Royal Society of Chemistry, supporting chemists in industry through training and professional development. Today, as we continue our synthesis module, Patrick will give us a high-level overview of carbonyl reactivity and take us through some of the key reactivity modes of this important functional group. And from there, I'll hand it over to you, Patrick. Thanks for coming on today.
Thanks, Matt, for the introduction, and thank you for having me to take part in the Synthesis Workshop Advanced Organic Chemistry course. Hi everyone, as Matt said, my name is Patrick, and in this episode, we'll be looking at the reactivity of the carbonyl group. As I'm sure you can appreciate, this is a huge and wide-ranging topic that covers a variety of interesting chemistry. Before we start, I should note that there is simply far more carbonyl chemistry than we can cover in detail in a single episode, so the aim of this talk is to provide a broad overview of the key reactivity modes of carbonyl compounds. Some of the material may be familiar to you, but I hope that recovering this will serve as a valuable reminder of the fundamentals of carbonyl chemistry before we introduce some of the more complex concepts. I would really encourage you to pause the video when you need to, and to use the references included throughout to learn more. Here is a summary of the topics we'll cover in this episode, and there are three general reactivity modes of carbonyls that we'll consider. The first is classical reactivity at the carbonyl carbon, through which carbonyl compounds react as electrophiles. Then we'll look at reactivity at the alpha position, where carbonyls are used as nucleophiles. And third, we'll consider the concept of Umpolung, or polarity reversal, as it relates to carbonyls. This is where strategies are used to reverse the typical electrophilicity of the carbonyl carbon, enabling carbonyls to be used as nucleophilic acyl anion equivalents. But first, I want to briefly emphasize the importance of the carbonyl group in organic chemistry. As you'll no doubt be aware, the carbonyl motif is ubiquitous in both nature and the laboratory, and therefore it is considered one of the most important functional groups in biological chemistry and organic synthesis. Here are just a few examples of naturally occurring and synthetically derived carbonyl-containing compounds, and I'm sure you can think of many more. The carbonyl group is characterized by a carbon-oxygen double bond, which is highly polar due to the difference in electronegativity between carbon and oxygen. The more electronegative oxygen atom draws electron density away from the carbon atom, creating a partial positive charge on the carbon. This partial positive charge makes the carbonyl carbon electrophilic, making it susceptible to attack by nucleophiles. When considering the many different types of carbonyl compounds, we can categorize them into two groups based on their structure and fundamental reactivity. In one group, we have aldehydes and ketones, which typically undergo nucleophilic addition to form alcohol products. In another group, we have carboxylic acids and their derivatives, including acyl halides, esters, acid anhydrides, and amides. Unlike aldehydes and ketones, these compounds contain functional motifs that can behave as leaving groups. Therefore, carboxylic acid derivatives undergo nucleophilic acyl substitution reactions, where, following initial nucleophilic addition, the leaving group is expelled, and the carbonyl functionality is reformed. We can also distinguish these two groups based on the oxidation level of the carbonyl carbon in each. With the double bond to oxygen, both aldehydes and ketones sit at oxidation level 2. The additional bond to a heteroatom in carboxylic acid derivatives means they are at oxidation level 3. For comparison, alcohols are at oxidation level 1. The concept of oxidation levels is helpful when considering the reactivity of not just carbonyls, but of organic molecules in general. It allows us to determine when a particular reaction is an overall oxidation or reduction process, and can help us identify what type of reaction is needed to convert one functional group into another. This is useful when carrying out retrosynthetic analyses and when planning the forward synthesis of complex molecules. Shown here is the general order of reactivity of the different classes of carbonyl compounds towards nucleophiles. As we might expect, the overall trend results from a combination of steric and electronic factors. For example, the carbonyl carbon in aldehydes exhibits both less steric hindrance and greater partial positive charge than in ketones, due to the absence of a second electron-donating R group. Therefore, aldehydes are more susceptible to nucleophilic attack than ketones. An important reaction of carbonyl compounds is their reduction via the nucleophilic addition of hydride equivalents. The products of these reactions are typically primary or secondary alcohols, although from amides you can see that we're able to access amine products. This is because, as we saw on the reactivity scale on the previous slide, the amine group is a poor leaving group, so instead, what was the carbonyl oxygen is kicked out following the first hydride addition. Note that aldehydes and ketones at oxidation level 2 are reduced via the addition of one hydride equivalent. Meanwhile, the carboxylic acid derivatives at oxidation level 3 are generally converted to their doubly reduced derivatives via addition of two hydride equivalents. In the latter case, the first reduction step forms an aldehyde, or for amines, an aminium intermediate, which readily undergoes a second reduction to form the reduced alcohol or amine products. However, we will look at how we can achieve partial reduction to aldehydes from carboxylic acid derivatives in just a moment. Now summarized here is the general reactivity of different carbonyl species with some commonly used reducing agents, where green indicates good reactivity, yellow, sluggish reactivity, and red means little or no reaction occurs. From this we can see that the choice of reducing agent can be important if we hope to achieve selective reduction in molecules containing multiple functional groups. For example, if we want to reduce an aldehyde or ketone in the presence of an amide, we can use sodium borohydride to form the primary or secondary alcohol, while keeping the amide intact. As I mentioned, we may also wish to achieve selectivity in terms of carrying out only partial reduction of a functional group. Specifically, how can we control the reduction of an ester or an amide so that only one hydride equivalent, rather than two, is added? One strategy is to use a more selective reducing agent, such as diisobutyl aluminium hydride or dibal, which is useful for the partial reduction of esters to aldehydes, provided the reaction conditions are also carefully controlled. Although this reaction is not general for all esters, using only one equivalent of dibal along with a low reaction temperature can help to ensure that only one equivalent of hydride is added. Unlike lithium aluminium hydride, which can in theory deliver up to 4 hydrides from one molecule, you can see from the structure of dibal that it contains only one hydride equivalent. As a result, it is much easier to control the stoichiometry of reactions using dibal. Make sure you are happy drawing out the mechanism of this reaction. It involves formation of an aluminium-coordinated hemiacetal intermediate, which is stable at low temperature. This is why a low reaction temperature is employed, as collapse of this intermediate in the presence of dibal could lead to over-reduction. The aldehyde product is then formed upon aqueous acidic workup, which also quenches any unreacted dibal. Similarly, tertiary amides can be partially reduced to aldehydes using lithium triethoxy aluminohydride. The ethoxy substituents in this reagent modulate its reducing power relative to that of the parent compound, lithium aluminium hydride. Several other reducing agents with different alkoxy substituents have also been developed, each displaying a different reducing ability, which can be exploited for the selective reduction of different carbonyl groups. In cases where we want to remove the oxygen functionality entirely, aldehydes and ketones can be fully reduced to alkanes. In the Wolff-Kishner reduction, the carbonyl compound is condensed with hydrazine to form a hydrazone. Treatment with base then induces reduction of the carbon with liberation of nitrogen gas. The basic conditions required for the Wolff-Kishner reduction make it a useful option for molecules containing acid-sensitive functionality. If base labile groups are present instead, a complementary approach is the Clemmensen reduction. Here, the aldehyde or ketone is treated with zinc amalgam and hydrochloric acid to form the corresponding alkane. The mechanism of this reaction is not well understood, but has been proposed to involve organozinc or zinc carbenoid intermediates. So now we've looked at the reduction of carbonyl compounds, now let's look at the reverse process, where we wish to generate carbonyls from alcohols via oxidation. Again, the correct choice of reagents and conditions can provide selective reactivity to access carbonyls at different oxidation levels. For example, the Jones oxidation employs chromium trioxide dissolved in aqueous sulfuric acid, which forms chromic acid in situ. This oxidizes secondary alcohols to ketones from which there is no possibility of further oxidation. Primary alcohols, however, are first oxidized to aldehydes, followed by further oxidation to carboxylic acids. This occurs via reaction of the initially formed aldehyde with water to form a hydrate, which is then oxidized by chromic acid. Similarly, the Jones oxidation can also be used to generate carboxylic acids from aldehyde starting materials. If we want to stop at the aldehyde, different reagents and conditions are required. Specifically, anhydrous conditions must be employed to avoid over-oxidation of the desired aldehyde product via hydrate formation. The Collins oxidation, which uses a complex of chromium trioxide with pyridine in dichloromethane, is effective for this. Related reagents that will perform the same transformation are PCC and PDC, whose structures are shown here. Due to their reduced reactivity, ease of handling, and commercial availability, the use of these reagents is typically preferable to the Jones or Collins oxidations. However, a major disadvantage of all these reactions is their use of highly toxic chromium-6 reagents. Safer, milder, and more environmentally friendly methods for carbonyl oxidation have therefore been developed. Examples include the use of hypervalent iodine reagents, as in the Des-Martin oxidation, or activated dimethyl sulfoxide, as in the Swern oxidation. Let's now look at the mechanism of nucleophilic addition to aldehydes and ketones. This is likely a recap of a mechanism that you're already familiar with, but it's useful to remind ourselves of the fundamental reaction before we move on to consider cases in which stereochemistry is a factor. The nucleophile attacks the carbonyl carbon to generate a tetrahedral alkoxide intermediate. Unless the incoming nucleophile is itself a good leaving group, this intermediate is relatively stable and does not collapse or react further. A subsequent protonation step, usually during an acidic workup, generates the alcohol product. A key feature of nucleophilic addition to carbonyls is attack of the nucleophile at the Bürgi-Dunitz trajectory, an angle of approximately 107 degrees relative to the carbonyl compound. This angle results from the maximum overlap of the nucleophile with the lowest unoccupied molecular orbital, or LUMO, which is the pi star orbital, combined with repulsion from the filled pi orbital of the carbonyl bond. As we have already seen, this general reaction occurs in reduction reactions with hydride sources. Another classic example is the Grignard reaction, in which more highly substituted alcohol products are generated via the addition of nucleophilic carbon groups from Grignard reagents. Where we have two different R groups in our carbonyl starter material, nucleophilic addition forms a stereocenter. In a simple case where there is no additional stereochemical information within either of the R groups, we would expect equal attack on either face of the carbonyl group, forming a racemic mixture of the two enantiomeric products. But what happens if we already have a stereocenter in our starting material, for example in the alpha position relative to the carbonyl carbon? In this case, the existing stereochemistry exerts an effect on the incoming nucleophile, and one possible diastereomer of the product will be favoured over the other. This is known as 1-2 asymmetric induction, since the asymmetry of the 2 position, the alpha position, induces formation of an asymmetric centre at the 1 position, the carbonyl carbon. We can predict which product will be formed preferentially using a stereochemical model known as the Falcon-Arn model. To apply this model, we must consider the most populated conformers of our starting material, along with the preferential direction of nucleophilic attack, accounting for the Bürgi-Dunitz trajectory as we do so. The first step is to label the substituents on the alpha carbon as large, medium, and small. Then, we redraw the molecule in a Newman projection. To make this easier, imagine you are viewing the molecule from the side, along the C1-C2 bond axis in the plane of the screen. When drawing the molecule in a Newman projection, the large substituent is drawn perpendicular to the carbonyl group, and can be placed either to the left or to the right. These represent the most sterically favourable and therefore most populated conformers of the molecule. Next, we must consider the preferred direction of attack of the nucleophile, remembering that it will approach the carbonyl group at the Bürgi-Dunitz angle of around 107 degrees. Not surprisingly, the nucleophile prefers to approach away from the large substituent, which leaves us with two possibilities: attack close to the small substituent, as shown at the top, or attack close to the medium substituent, shown below. Again, the minimization of steric repulsion is key, and attack close to the smallest group is preferred. We can draw out both possible products in their Newman projections, with the C1 and C2 substituents now in a staggered conformation, and the nucleophile added to the carbonyl carbon on the side of its attack. We can then redraw the products as normal structures, showing the new stereochemistry using wedged and hash bonds. It's important to be careful when converting the structure from its Newman projection back to the standard depiction. Practicing some examples with the aid of a molecular model kit can be helpful for this. There are, however, exceptions to the Falcon-Arn model, but these too can be explained by considering the stereoelectronic interactions involved. The first of these modifications, referred to as the polar Falcon-Arn model, is that in cases where there is an electronegative group on the alpha carbon, the electronegative group is treated as though it were the large substituent. Therefore, we place the electronegative group X perpendicular to the carbonyl carbon instead of the most sterically congested group. The reason for this is that, while these are not the most populated conformers, they are the most reactive. This is because the perpendicular arrangement of the carbonyl and the electronegative group maximizes overlap between the lowest unoccupied molecular orbital of each group. The pi star orbital of the carbonyl group, overlaps with the sigma star orbital of the electronegative group X, producing a new LUMO which is lower in energy and therefore more susceptible to nucleophilic attack. As before, we can then consider the preferred trajectory of the nucleophilic attack, taking into account the Bürgi-Dunitz angle. Here we have just directly replaced the large group with an electronegative group, so the stereochemical outcome of the reaction is the same as before. Another modifying case is where there is a heteroatomic group at the alpha position of our starting material and a chelating agent in the reaction mixture. Here we apply another model called the Cram chelation model, where the chelating metal holds the carbonyl group and the heteroatomic group in close proximity. We can see that the two groups are almost eclipsing one another. This chelation locks the conformation of the molecule as shown, and we can then consider from which side the nucleophile will prefer to attack. As in the previous cases, nucleophilic attack nearest to the smallest group is preferred. Reactions involving Lewis acids of highly charged metal ions, such as those shown at the top, will typically chelate to suitable substrates. Lithium ions may also be involved in chelation, while sodium and potassium typically are not. Stereoinduction can also extend beyond the alpha position. In particular, the stereoelectronic environment at the beta carbon, the 3 position, can direct 1,3 asymmetric induction. For cases of 1,3 stereoinduction not involving metal chelation, a model proposed by Evans is a good predictor of the stereochemistry of the favoured product. In the proposed transition state, the beta stereocenter is placed away from the incoming nucleophile to minimize steric interactions. This is similar to the positioning of the large substituent in the Falcon-Arm model. The electronegative X group at the beta stereocenter is oriented so that its dipole opposes that of the carbonyl group to reduce dipole interactions. The R group of the beta position is also oriented away from the carbonyl group to minimize steric hindrance. The major product from non-chelate 1,3 stereoinductions typically has the newly formed alcohol and the electronegative group X positioned on opposite sides of the product, in a so-called anti-relationship. Therefore, the major products of these reactions are typically referred to as anti-products, while the minor products are syn, with the two groups on the same side. Take care, however, when applying the terms syn and anti, as they only refer to the relative relationship of two defined groups. These terms should always be used in conjunction with structural drawings where the relative orientation of the relevant groups is clear. Reitz has also demonstrated that the Cram chelate model can be extended to 1,3 asymmetric induction. We will not be covering this model here, but I've included the reference at the bottom if you're interested in learning more. We'll now move on to look at our second mode of carbonyl reactivity, which is chemistry that takes place at the alpha carbon. Aldehydes and ketones can be converted to their enol form, provided there is a proton at the alpha position. In other words, they must be enolizable. Enols are structural isomers of the so-called keto form we're used to seeing, and are generated via proton shift from carbon to hydrogen. Since the two forms are in equilibrium and can readily interconvert, they are known as tautomers, and conversion between the two is called keto-enol tautomerism. This process can be catalyzed with acid or base, as both can facilitate proton transfer. Check that you are happy drawing out both the acid and base catalyzed mechanisms of keto-enol tautomerism. In cases where there are no alpha protons present, the enol cannot be generated, and these carbonyl species are said to be non-enolizable. The keto-enol equilibrium generally favours the keto form, typically by a factor of around 10 to the 5 or more for aliphatic ketones. This is mainly due to the difference in bond strengths between the carbon-oxygen and carbon-carbon double bonds. However, as with other equilibrium reactions, the keto-enol ratio is also influenced by factors such as substitution, conjugation, hydrogen bonding, and aromaticity. For example, the enol form of acetylacetone is stabilized by hydrogen bonding, and in the pure material, the enol is favored over the keto form by 4 to 1. However, this equilibrium is highly solvent and temperature dependent, and in polar solvents such as water, in which there is more competition for hydrogen bonding, the equilibrium favors the keto form. An extreme case that highlights the influence of aromaticity is phenol. We never really consider the keto form of phenol, since it exists exclusively in the enol form, which is stabilized by the aromaticity of the ring. Enols are typically formed under equilibrating conditions. For unsymmetrical ketones, where there is a choice of different possible enols that may be formed, equilibration will lead to preferential formation of the most thermodynamically stable enol. This is the one in which the carbon-carbon double bond is most substituted. Enols are nucleophilic at the alpha carbon due to pi donation of a lone pair of electrons from oxygen. This is demonstrated by the resonance form in which the negative charge is placed on the alpha carbon. Enols are also nucleophilic at oxygen, but most of their interesting and useful chemistry occurs at the alpha carbon. For example, enolizable ketones undergo alpha bromination, reacting with electrophilic bromine via the formation of the nucleophilic enol under acid catalysis. Enolates are the conjugate bases of both carbonyls and enols, and are formed under basic conditions via abstraction of an alpha proton. Enolates are relatively stable species due to delocalization of the negative charge between the oxygen and the alpha carbon via resonance. They are typically depicted as their major resonance contributor with a negative charge on the oxygen atom. However, they tend to react as carbanions, adding into electrophiles to provide a range of alpha-substituted carbonyl products. Due to their negative charge, enolates are more nucleophilic than their neutral enol counterparts, so they are generally more synthetically useful. Enolates can be generated from a variety of carbonyl compounds, provided they have alpha protons. The ease with which the enolate can be formed is correlated with the acidity of the alpha proton, which is itself dependent on the stability of the resulting enolate. For example, diketones, beta-ketoesters, and diesters have two electron withdrawing groups that can readily stabilize a negative charge at the alpha position. Therefore, the alpha protons in these carbonyl compounds are relatively acidic, and enolate formation occurs more easily than for aldehydes and ketones. By contrast, the alpha protons in esters and amides are less acidic than those in aldehydes and ketones, which means the enolates of esters and amides are more difficult to form. This is due to pi donation from the ester oxygen or amide nitrogen atom, which destabilizes the negative charge in the enolate. To learn more about pKa values and how structure can be used to determine relative acidity and reactivity, check out episode 1 of this course, in which Emily Wearing provides an excellent overview of acids and bases. As we saw for enols, unsymmetrical ketones offer the possibility of forming two different enolates. We can control which enolate will be formed using different conditions and bases. Thermodynamic control involves the formation of the most thermodynamically stable, more substituted enolate via removal of the proton shown in red. This position is more sterically hindered, so deprotonation will occur more slowly, but the resulting enolate is the most stable. Therefore, under equilibrating conditions, this enolate will ultimately be formed. Treatment of a ketone with an alkoxide base can be used to access the so-called thermodynamic enolate. To achieve formation of the less thermodynamically stable enolate under kinetic control, rapid deprotonation at the less hindered position, shown in blue, is required. This can be achieved using a very strong bulky base such as lithium diisopropyl amide, or LDA, at low temperature. This slows the rate of deprotonation at the more substituted position to the point where only the less substituted enolate forms. This is referred to as the kinetic enolate. LDA can be used for the deprotonation of ketones, esters, and amides. Ketone enolates are good carbon nucleophiles and can be employed in reactions with a variety of electrophiles. For example, like enols, they will react with bromine to afford alpha-bromo-carbonyl compounds. Unlike enols, however, ketone enolates can undergo alpha alkylation, which is a useful method of forming new carbon-carbon bonds. The carbonyl is usually first treated with a strong bulky base like LDA to ensure complete enolate formation. The enolate is then reacted with an alkyl halide to form the alpha alkylated product. Stereoselective alpha alkylation can be achieved by introducing a chiral element into the carbonyl starting material. One of the most effective methods to achieve this is by using Evans auxiliaries, which were first developed by Dave Evans in the 1980s. These chiral auxiliaries are oxazolidinones, whose stereochemistry is derived from readily available sources. Shown here are the first two enantiocomplementary auxiliaries introduced by Evans. The first is derived from the natural amino acid valine, and the second is synthesized from a commercially available enantiomer of norephedrine. Today, several oxazolidinones are commercially available in both enantiomeric forms. The first step in the use of an auxiliary agent is its installation into the substrate of interest. Evans auxiliaries are introduced into carbonyls via acylation. The oxazolidinone is typically deprotonated with Bewley at -78 degrees, followed by reaction with an acyl chloride. This generates an imide product whose reactivity is closer to an ester than an amide in terms of its acidity, enolate nucleophilicity, and cleavage chemistry. With the chiral auxiliary installed, a diastereoselective alpha alkylation reaction can then be carried out, in which the auxiliary influences the stereochemistry at the newly formed stereocenter. The imide is first deprotonated at the alpha position, typically with LDA. An important consideration here is the geometry of the enolate, which can exist as the E or the Z form, as this will determine the stereochemical outcome of the reaction. Enolate geometry is influenced by several factors, including the substrate itself, the base used for deprotonation, and the solvent used in the reaction. We won't look at this in more detail here, but the key point to know is that deprotonation of imides with LDA reliably generates Z enolates with very high selectivity. Reaction of the Z enolate with an alkyl halide affords the alpha alkylated product. The electrophile is directed to one face of the enolate, in this case the back face, due to the sterically bulky isopropyl group of the auxiliary blocking the front face. These reactions generally occur with very high diastereoselectivity. Following the alkylation reaction, removal of the auxiliary is required. A variety of conditions can be used to generate different carbonyl groups for further functionalization. Shown here are just two possible methods. The first is oxidative hydrolysis with lithium hydroperoxide to generate a carboxylic acid product. The second is conversion to a Weinreb amide via reaction with NO-dimethyl hydroxylamine. Weinreb amides are especially useful products as they react with organometallic reagents to form ketones without the issue of over-addition observed with other carboxylic acid derivatives. In the references, I've included a review article about Weinreb amides if you'd like to learn more. A more recent example of asymmetric carbonyl functionalization is the enantioselective alkylation of aryl and heteroaryl acetic acids, developed by Zakarian in 2011. A distinct feature of this approach compared with Evans-type alkylation is the traceless nature of the auxiliary, which forms a non-covalent complex with the enolate as an intermediate during the reaction, but does not appear in the starting material or the product. Therefore, additional synthetic steps for the installation and removal of the auxiliary are avoided. The reaction proceeds through formation of an ene diolate by a double deprotonation of the carboxylic acid substrate with N-butyl lithium. Since ene diolates are symmetrical, EZ selective enolization is not a factor here. The chiral diamine auxiliary is also doubly deprotonated to form a dilithium amide. This explains why 4 equivalents of N-butyl lithium are required for efficient reactivity. The ene diolate and dilithium amide form a non-covalent complex in solution which directs addition of alkyl electrophiles to one face of the ene diolate. Due to the high nucleophilicity of ene diolates, typically unreactive and hindered alkyl halides afford high yields and enantioselectivities in this reaction. Using experimental and computational techniques, structural studies of the organolithium aggregates formed during the reaction allow a stereochemical model to be proposed. The dienolate and dilithium amide form a tetralithio aggregate comprised of the 2 dianions as shown. The dilithium amide controls the orientation of the dienolate, with the phenyl group in red pointing up and to the right as shown. This orientation is energetically more favorable than other possible aggregates, with steric clashes between the dienolate, amide, and solvated lithium ions minimized. The dilithium amide also blocks one face of the dienolate, restricting electrophilic addition to only the front face. In combination, these effects lead to the high enantioselectivities observed in the reaction. One of the most powerful reactions involving carbonyl compounds is the aldol reaction, which is the addition of an enolate nucleophile to another carbonyl species as the electrophile. This generates a new carbon-carbon bond between 2 carbonyls and forms beta-hydroxycarbonyl compounds as products. The aldol condensation, in which water is eliminated from the initial beta-hydroxycarbonyl product, generates alpha-beta unsaturated carbonyls. Aldol reactions and condensations can be performed with a variety of substrates and bases, but to achieve selective crossed aldol reactions, in which 2 different carbonyl species are coupled together, care is needed to avoid complex mixtures of products. One approach, shown here for the coupling of a ketone with an aldehyde, is to first form the ketone enolate quantitatively by addition of the ketone starting material to an excess of strong base, such as LDA. The enolate is then reacted with the aldehyde electrophile to form the aldol product. A variety of aldol-type reactions have been developed, all involving the same general reaction of an enolate nucleophile adding into a carbonyl electrophile to generate a new carbon-carbon bond. Some examples are shown here, along with some references for further reading. Aside from carbon-carbon bond formation, another useful feature of the aldol reaction is the formation of two new stereogenic centers at the positions alpha and beta to the carbonyl group. The relative stereochemistry at these positions may be syn or anti, so now we'll look at how this can be rationalized using transition state models. In 1957, Zimmermann and Traxler proposed a mechanistic model to explain the diastereoselectivity of aldol reactions with metal enolates. They invoked a six-member chair-like transition state for these reactions, which can explain the relative stereochemistry of the two new stereocenters formed. The first thing to consider is the geometry of the enolate, which may be formed as the Z or the E isomer. This is important as the enolate geometry defines the stereochemistry of the alpha position in the aldol product. As we touched on when looking at asymmetric alkylation reactions using Evans auxiliaries, enolate geometry can be influenced by a number of factors, including the substituents of the carbonyl substrate, as well as the metal, base, and solvent used for enolate formation. We won't look at this in more detail here, but it's useful to know that enolate geometry can often be controlled with excellent selectivity for either the E or the Z enolate by modifying the reaction conditions used. This is particularly the case for boron enolates, which have been widely employed in aldol reactions. Take a look at the references if you'd like to learn more. So starting with the Z enolate, we can look at the possible chair-like transition states for addition to an aldehyde, and consider which is more energetically favourable. This will allow us to determine the relative stereochemistry in the product. In each transition state shown, the metal ion M is coordinated to both the enolate oxygen and the carbonyl oxygen of the approaching aldehyde electrophile, shown in blue. The red dotted bond indicates the newly forming carbon-carbon bond. The difference between the two transition states is the orientation of the aldehyde, which governs the stereochemistry of the beta center. In the favoured transition state, the R1 group of the aldehyde is oriented in a pseudo-equatorial position, which minimizes 1,3 diaxial interactions with the R group of the enolate. Compare this with a disfavored transition state, where there is a clear steric clash between the two R groups. In the favored transition state, the methyl group of the enolate and the aldehyde oxygen, which becomes the hydroxyl group in the product, are positioned on the same face of the chair, in this case both pointing down. This is carried through to the product, where they are on the same face of the molecule. Therefore, Z enolates lead to syn aldol products. For the E enolate, we can construct two analogous transition states. Again, the aldehyde is oriented to minimize 1,3 diaxial interactions, with the R1 group in a pseudo-equatorial position. This time, due to the different enolate geometry, the methyl group points towards the upper face of the chair, while the aldehyde carbonyl is pointing down. Therefore, the methyl and hydroxyl groups are on opposite sides of the product, so E enolates lead to anti-aldol products. It's important to note that for each of the transition state models shown, there is an enantiomeric transition state that is, by definition, of equal energy. The syn and anti-diastereomers shown are each formed as racemic mixtures of their two enantiomers. In order to differentiate between two syn or two anti-transition states, a chiral element must be introduced, which will generate diastereomeric transition states of different energies. Chirality can be incorporated into the enolate, the aldehyde, or the coordinating metal species. All three of these approaches are possible, but we will look at just the first of these in this talk. As we have already seen for enolate alkylation reactions, Evans auxiliaries are powerful tools in the enantioselective functionalization of carbonyls. They can also be applied as chiral elements in aldol reactions, leading to preferential formation of one diastereomer of either the syn or the antiproduct formed. Since a single enantiomer of the Evans auxiliary is used, one enantiomer of the aldol product is formed selectively. In the example shown, treatment of the Evans imide with dibutyl boron triflate as the Lewis acid and Hunig's base leads to selective formation of the Z enolate. As predicted by the Zimmermann-Traxler transition state model, the Z enolate leads to the syn product, in this case with the methyl and hydroxyl substituents pointing away from us as drawn. To understand why this enantiomer is favoured over the other, in which the two groups are pointing towards us, we can look at the possible chair-like transition states, this time with the Evans auxiliary incorporated. In both transition states shown, the auxiliary group is oriented so that dipole-dipole interactions are minimized. In the favoured conformation, the bulky benzyl group is pointing away from the chair, while in the disfavoured transition state, it clashes with it. This leads to preferential formation of the syn-aldol enantiomer shown. By varying the chiral auxiliary along with the conditions used to form either the E or the Z enolate, it's often possible to access all 4 enantiomeric aldol products with high levels of stereo control. This approach has been widely employed in the total synthesis of complex natural products. Alternatives to enolates are enamines, which can be used as enolate equivalents in alpha functionalization reactions of carbonyl compounds. Enamines are formed via condensation of a secondary amine with an enolizable aldehyde or ketone, often in the presence of an acid catalyst. Like enols and enolates, enamines are nucleophilic at the alpha carbon, as demonstrated by the resonance structure shown. In terms of relative nucleophilicity, enamines are more nucleophilic than enols, but less nucleophilic than enolates. Enamines undergo nucleophilic addition into a range of carbon nucleophiles. They react with Michael acceptors via conjugate addition to generate 1,5-diketones, and with acyl halides via nucleophilic acyl substitution to form 1,3-diketones. Activated sp3 electrophiles, such as benzylic and allylic alkyl halides, are also reactive. However, reactions of non-activated alkyl halides, such as simple primary alkyl halides, are generally lower yielding. As you can see, the initially formed products of these reactions are aminium ions. The carbonyl products are readily revealed via hydrolysis during aqueous workup. Catalytic enamine chemistry, and in particular asymmetric enamine catalysis, is also possible. By employing catalytic quantities of a chiral amine, a stereochemically biased enamine can be generated. The naturally occurring and therefore readily available amino acid proline is especially useful for this, providing both a nucleophilic amine for enamine formation and an acid-base co-catalyst in the form of the pendant carboxylate group. Proline-based catalysis was developed as early as the 1970s, and since the year 2000, it's received significant attention for its ability to generate a range of carbonyl coupling products in a mild, non-toxic, and selective fashion. This ultimately led to the awarding of the Nobel Prize in Chemistry for 2021 to Ben List and David Macmillan for their independent contributions to the field of asymmetric organic catalysis. A seminal example of proline-based enamine catalysis, reported by Barbus, Lerner, and List in 2000, is the use of proline to catalyze the direct asymmetric aldol reaction between acetone and a variety of aldehydes. The yields and enantioselectivities in this initial report were generally moderate, but this paved the way for subsequent studies in which excellent yields and enantioselectivities were achieved for certain carbonyl substrates. A 9-membered cyclic transition state is proposed, in which an enamine is formed between the proline catalyst and acetone, and the carboxylate group of proline is coordinated to the aldehyde electrophile via hydrogen bonding. This hydrogen bonding interaction both activates the incoming electrophile and guides its approach from the upper face of the enamine, leading to the enantioselectivity observed. Significant contributions to the field of asymmetric enamine catalysis were made independently by Hayashi and Jorgensen, who introduced diaryl prolinol silyl ether-based catalysts for the enantioselective alpha functionalization of aldehydes. In these catalysts, the carboxylic acid of proline has been replaced with a bulky aryl and silyl ether groups. Therefore, enantioselectivity is achieved not through hydrogen bonding, but instead by steric shielding. Specifically, the sterically bulky groups both control the geometry of the enamine and block one of its faces, directing the approaching electrophile to the opposite face. Notably, this alternative mode of steric control provides complementary reactivity compared to proline. For example, the alpha amination of aldehydes with azo dicarboxylates can be achieved using both proline and Hayashi-Jorgensen type catalysts, leading to products with inverted absolute configuration, even though the absolute configuration of the catalysts is the same. The Hayashi-Jorgensen catalysts are generally more active and more soluble in organic solvents than proline. Their improved properties have enabled their application in a range of asymmetric alpha functionalization reactions. A variety of carbon and heteroatom-based nucleophiles can be used, typically affording products in good yields and excellent enantioselectivities. We'll now look at the third and final key reactivity mode of carbonyl groups, and that is Umpolung reactivity at the carbonyl carbon. Umpolung is a German word meaning polarity reversal, and its use in chemistry was introduced by Dieter Seebach and E.J. Corey to refer to synthetic strategies involving the reversal of typical or expected reactivity at a given functional group. This is a very powerful concept in retrosynthetic analysis and complex molecule synthesis, as it allows us to incorporate transformations that aren't possible using so-called normal modes of reactivity, such as those we have looked at so far. In the context of carbonyl compounds, Umpolung chemistry is used to reverse the polarity and reactivity of the typically electrophilic carbonyl carbon to make this position nucleophilic. Through Umpolung chemistry, carbonyl species can be employed as acyl anion equivalents, where the carbonyl carbon can be considered to possess a negative charge that will readily react with electrophilic species. We'll look at two general ways to achieve this overall process. The first is a stoichiometric method, using 1,3-dithione protecting groups as Umpolung agents. The second is a catalytic approach, using cyanide-type Umpolung chemistry. This includes the use of cyanide anion itself, as well as N-heterocyclic carbene catalysts which react in a similar fashion to cyanide. Aldehydes are converted to 1,3-dithiones, which are cyclic thioacetals with a bridging propylene moiety, by double nucleophilic addition of 1,3-propane dithiol. This is analogous to acetal formation with diols. Unlike acetals, however, 1,3-dithiones are resistant to hydrolysis and strong bases. The thioacetal group also acidifies the carbonyl proton sufficiently for deprotonation by very strong bases. Butyl lithium is typically used as a base, generating the lithium dithione species shown. This can be thought of as a masked acyl anion, as the polarity of the carbonyl carbon, which is now very nucleophilic, has been reversed. Reaction of the lithium dithione with a carbon electrophile generates a new carbon-carbon bond. This overall process is known as the Corey-Seebeck reaction, named after Corey and Seebeck, who developed the Umpolung chemistry in the 1960s. Removal of the thioacetal group to regenerate the carbonyl and reveal the ketone product requires oxidative deprotection conditions. This is one of the major drawbacks of 1,3-dithione Umpolung chemistry, as this deprotection step can be challenging and cumbersome. Mercury oxide is typically used, exploiting the high affinity of mercury-2 for thiolates. More modern deprotection methods include the use of hypervalent iodine reagents. The lithiated 1,3-dithiones can be alkylated with a range of carbon electrophiles, including alkyl halides, epoxides, ketones, acyl halides, and aminium salts. Following oxidative deprotection of the dithione group, a variety of functionalized ketones are generated. An early example of Umpolung chemistry of carbonyl compounds is the benzoin condensation, which was first reported in the 1830s. The classical reaction is the coupling of two units of benzaldehyde to form benzoin, in which the carbonyl and hydroxyl groups have a 1-2 relationship. The benzoin condensation is catalyzed by the cyanide anion and involves formation of a nitrile enolate intermediate that can be thought of as our acyl anion equivalent. This species can undergo nucleophilic addition to an electrophile, in this case a second equivalent of the benzaldehyde starting material. The mechanism of the benzoin condensation was elucidated in the early 1900s, and involves initial nucleophilic addition of the cyanide anion to the electrophilic carbon. This results in formation of a cyanohydrin which, upon deprotonation under basic conditions, affords our acyl anion equivalent. As highlighted by the partial charges shown, the polarity of the carbonyl carbon has been reversed, and it has gone from being electrophilic in the carbonyl starter material to nucleophilic in the nitrile enolate. In other words, we have achieved polarity reversal, or Umpolung. The nitrile enolate nucleophile then attacks the electrophilic carbonyl carbon of a second equivalent of benzaldehyde in the key 1,2 carbon-carbon bond-forming step. Subsequent proton shift, followed by elimination of cyanide anion to regenerate the catalyst, forms the benzoin product. A related area of Umpolung carbonyl chemistry is the use of N-heterocyclic carbenes, or NHCs, which catalyze the benzoin condensation, as well as many other reactions. The use of NHC catalysts stems from the discovery by Ugai in 1943 that the benzoin condensation can be catalyzed by thiamine instead of cyanide. Thiamine exists in nature as the enzyme cofactor thiamine diphosphate, where it's responsible for the generation of acyl anion equivalents in a number of biochemical processes. This species, along with several other simpler thiazolium salts, were demonstrated to be effective catalysts in the benzoin condensation. The acyl anion equivalent in this case is an enaminol, known as a Breslow intermediate, named after Ronald Breslow, who first elucidated the mechanism of the thiazolium-catalyzed benzoin condensation in the 1950s. This intermediate is structurally similar to the nitrile enolate we saw in the cyanide reaction, and the resonance form shown here has the negative charge placed on the carbonyl carbon to emphasize its acyl anion-like nature. The Breslow intermediate forms via initial deprotonation of the thiazolium salt to form the active catalyst, the N-heterocyclic carbene. This nucleophilic carbene reacts with the electrophilic aldehyde substrate to form the enaminol. Since the carbonyl carbon is now nucleophilic, it reacts with another equivalent of the aldehyde, as we saw for the cyanide catalyzed reaction. Since these early discoveries, the field of NHC catalysis remained largely unexplored until a huge increase in interest in the late 1990s. In the context of acyl anion chemistry, asymmetric variants of the benzoin condensation have been developed by Enders, Connon, and others. Key to the stereoselectivity of these reactions is the use of N-aryl bicyclic triazolium salts, whose steric and electronic properties can be tuned through structural modifications. In the example shown, the alcohol in the NHC catalyst acts as a directing group, providing an additional mode of catalytic control that leads to exceptionally high enantioinduction. So in summary, we've looked at an overview of three key aspects of carbonyl chemistry. We've seen how the electrophilic carbonyl carbon reacts with nucleophiles, how the nucleophilic alpha position reacts with electrophiles, and how the electrophilic nature of the carbonyl carbon can be reversed to generate acyl anion equivalents through Umpolung chemistry. As I said at the very start, there's much more to carbonyl chemistry than we've covered here, but I hope this talk has inspired you to learn more. If you'd like to know more about any of the topics we've covered in this lesson, or if there are areas of carbonyl chemistry we didn't cover that you're keen to discuss, please leave your questions in the comments and I'll do my best to answer them. I hope you enjoyed the talk, and thanks very much for watching.
Thanks a lot, Patrick, for a great talk. Tune in for our next installment of this course as we continue our synthesis module and learn about protecting groups. See you next time.